In this lecture, I'll be introducing the various basic terminologies of trees. So why do we need trees? Data that we have is not always of linear type. So whenever you have non-linear data, then there are high chances that we might have to use some other kind of data structure apart from stacks, queues, linked list. So there we may have to use some structure like a tree. Whenever the linear access time for linked list is too high, then also we might have to use trees. So then you group the data into a tree-like structure. Also, whenever we have some data in a hierarchical trend, okay, we can generate a hierarchical relationship among the data elements that we have. For example, if you have some data record that has some hierarchical relationship, like a family tree, grandparents, parent, child. So when you have some data like that in the form of a data record, then we definitely have to use trees. The worst case time complexity is of the order of log n. So that is one advantage whenever we use trees mostly. Now, trees can be defined in many ways. The most easiest way is using recursion. Trees consist of a collection of nodes arranged in a hierarchical pattern. So here a tree has a root node. The others are the various subtrees. Okay, left subtree, then you have another subtree and so on. Here also you have A is a root node, then it has children node like B, C, D, E, F, G, and grandchildren nodes H, I, J, and so on. So when I say that it is not a tree is when the siblings are connected. So D and E are siblings, they are connected. So you don't call this as a tree. This is called a graph. So there are so many terminologies when it comes to tree. So the first one is root. The starting node of a tree is called the root, and there is only one root node in any tree. So this root node has two children, B and C. Edges. So nodes are connected using the link called edges. Here in this picture, A is connected to B using an edge. B is connected to E using an edge. And in any tree, when you have n nodes, you will have exactly n minus 1 edges. So here in this picture, 1, 2, 3, 4, 5, 6. We have 6 nodes and we have 5 edges. Edges are 1, 2, 3, 4, 5. So we have 6 nodes and 5 edges here. Next is parent. So the node that have children nodes or have branches connecting to other nodes is called a parent. So here A is the parent of B and C, and B is the parent of D and E. F is the child of D, which means D is the parent of F. So parent nodes have one or more children node, then only it is called a parent node. So by default, the leaf node should have a parent, or root if it has a child. If it is a tree with only one node, which means the root node is not having any child. Otherwise, if we have more than one node, then obviously the root will be a parent. Next is a child. So the node that is descendant of any node is a child. So this C is descendant of A, which means C is the child of A. All nodes except the root node is a child node. F is a child of D, D is a child of B, B is a child of A, and so on. Next is siblings. So when two or more nodes have the same parent, you call it sibling. So here in this case, B and C have the same parent A. So they are called siblings. D and E have the same parent B. So they are called siblings. And one important point to say that this is a tree is the siblings are not connected by an edge. If the siblings are connected by an edge, then you call it a graph. It is not a tree, definitely. Next is degree. So the definition is the number of children per node is the degree of the node. So A has 2 children, which means the degree of A is 2. B has 3 children, so degree of B is 3. C does not have any child, so degree of C is 0. D does not have any child, E does not have any child, and F does not have any child. So degree of D, E, F, all that is 0. The degree of the complete tree is the highest degree of all the nodes among all the nodes. Whichever node has the highest degree, then that degree is the degree of the tree. So here in this case, if you see, B has the highest degree of 3. So the degree of the entire tree is 3. Internal node. The node with minimum one child is called a internal node. It is also called as non-terminal node. So by default, all the leaf nodes are called as terminal nodes. So leaf nodes does not have any child. So it is not definitely a internal node. The other nodes apart from the leaf nodes are called as internal node. Next is leaf node. Node with no child is called a leaf node. So here in this case, C is a leaf node, D is a leaf node, E is a leaf node, F is a leaf node, and B is a internal node. Next is level. So each step of a tree is a level number starting with root as 0. So A is the root. So A is at level 0. Its children, immediate children, they are at level 1. Its immediate children, they are at level 2. And its immediate child, they are at level 3. So starting from root, which is at level 0, then next step, we have the next level. This is the term called level in a tree. Next terminology is height. The number of edges in the longest path from the node to any leaf is the height of the tree. So in this image, you can see that this is the longest path. So obviously, this is the height of the tree. This determines the height of the tree. Now, height, as usual, when a child is a baby, so we um, measure the height of the baby or the child from bottom up. Similarly, leaf nodes, all the leaf nodes, their height is 0. So height of C, G, E, F, C, G, E, F, all that is 0. Height of D. So we calculate it from the bottom. So there is only one edge to D from the leaf node. So height of D is 1. Height of B is 2 because there are two edges from the leaf node. 1, 2. Height of A is 3. 1, 2, 3. So the height of each node is calculated from any leaf node. And the height of the tree is from any leaf node till the root node, how many number of edges, the maximum number of edges covered is the height of the tree. So height of this tree is 3 because of this longest path. The next terminology is depth. So this is the vice versa of height, which is depth is always calculated from the surface deep within. So from the surface of the ground, say for example, if you keep digging, the depth we calculate, we have gone 1 meter, 2 meter and so on. So that is the depth here in the tree as well. So we calculate the depth from the root node till the leaf node. Number of edges from the root node to any particular node is the depth. So depth of root node is 0. And usually depth of the leaf nodes are the highest. It depends on how long it travels from the root node. So depth of the tree is depth of the longest path from the root to a particular leaf. Here in this case, depth of B is 1 because from root node we traverse to B, edge is 1. Depth of C is also 1 because we have one edge connecting the root node to this node. Now depth of D. From root node we have two edges, 1, 2. So depth of D is 2. Similarly, depth of E and F is 2 because from A, which is the root node, we have to calculate how many number of edges are connecting to E or F. So 1, 2, 1, 2. So the depth of D, E, F is 2. Now depth of G. Depth of G is calculating from root node. The path that leads to G is 1, 2, 3. So we have 3 edges covering from the root node till G. So depth of G is 3. Now amongst all the depth, you can see that this is the greatest value. So the depth of the tree is 3. Subtree. So just like how we learn in set language, sets. So if you have 5 elements, the various sub combinations are the subsets. Similarly, if this is the whole tree, taking this part alone is a subtree. Excluding B, this part alone is a subtree. G alone is a subtree. E alone is a subtree. CH is a subtree. So apart from the root, if you take the left part completely, that is one subtree. Apart from this root, if you take the left part, that is a subtree. Apart from this root, if you take this one, this is a subtree, and so on. So each child of a tree forms a subtree recursively. Next is a forest. Set of disjoint trees is a forest. So there is no connection, no similarity between this tree and this tree. So they form a forest. Next is a path. So a path from any node, say A1 to AK, is defined as a sequence of nodes such that AI is the parent of AI plus 1 for any I which is greater than 1 and less than K. So here path between A and G. So path between A and G is AB DG. So this is the path. Next is length of the path. Length of the path is the number of edges in that path. So consider A to G. So the path is A to B, B to D and D to G. So the length is 1 edge, 2 edge, 3 edge. So the length of the path is 3 when it comes to A to G. Ancestors and descendant. So if you take any node, say for example B. So for B, the ancestor is A. The descendant of B is D, E, F. So the children and below, they are the descendants, and parent and above, they are the ancestors. So by definition, if there is a path from A to B, then A is an ancestor of B and B is the descendant of A. Now there are various types of trees. These are the most common trees: general tree, forests, binary search trees, expression trees, tournament trees, and there are so many. So why should we learn trees? There are several applications. Trees are used to store simple as well as complex data. When we say simple, it can be an integer value, a character value, and or it can be any simple primitive data type value. Complex data means it can be a record of data, a row of data, a structure of data, and so on. Trees are often used for implementing other data structures like hash table, sets, maps, and so on. Then coming to a self-balancing tree like a red-black tree. A red-black tree is used in kernel scheduling to preempt massive multiprocessor computer operating system use. Another variation of tree, say B tree, they are predominantly used to store tree structures on disks. B trees are also used for secondary indices in databases where the index facilitates a select operation to answer some range criteria. Trees are important data structure used for compiler construction. Trees are also used in database designs and are used in file system directories. Trees are also used widely where information storage and retrieval are very essential in symbol tables and so on. So in this lecture, we have discussed the various basic terminologies of trees like root, edge, parent, child, sibling, degree, internal node, leaf node, level, height of a tree, depth of a tree, subtree, forest, path, ancestor, descendant, and also the various applications of trees. Thank you.